Welcome to the HPC Best Practices webinar series. This series is brought to you by the IDEAS Productivity Project, which is part of the exascale computing project of the US Department of Energy. This series is a collaboration involving the computing facilities at the Argonne, Oak Ridge, and Lawrence Berkeley National Laboratories. I'm Osni Marquez from Lawrence Berkeley Lab, and I'll be the host for today's webinar, Mining development data to understand and improve software engineering processes in HPC projects. The webinar will be presented by Boyana Norris from the University of Oregon. Boyana received her Bachelor's in Computer Science at Wake Forest University in 1995 and her PhD in Computer Science from the University of Illinois at Urbana-Champaign in 2000. She worked at Argonne National Lab from 1999 through 2003 as a postdoc, assistant computer scientist, and computer scientist. Currently, she's an associate professor at the Department of Computer and Information Science at the University of Oregon. Her research focuses on methodologies and tools for performance reasoning and automated optimization of scientific applications to ensure continued or better usability of HPC tools and libraries, and also to improve developer productivity. We have issued more than 90 tickets for this webinar, and all attendees have been muted. We'll be receiving questions through the Zoom chat and also the Google Doc, whose address I have pasted the Zoom chat. I'm going to do it again for those who joined us a little bit later. The webinar will have breaks so the speaker can respond to the questions that come in. Boyana, let's stop my sharing and please.
Thank you for the really nice introduction. Can you see my screen, Osni?
Yes.
Okay, great. So thank you very much for being here. I will dive right in. Our motivation for the tools and methodologies that I'm going to talk about today are, we have several motivations. We realize that software development productivity is affected by many factors, many of which are difficult or impossible to measure accurately. And so what we do, instead of worrying about that and those factors, we focus on things we can measure, and we try to evaluate them and figure out if they can help us understand how software practices the developers follow affect various observable metrics of productivity. And we are developing tools as we go along, which are meant to be used. So I will show some examples, but really the hope is that you, the community, will become excited and participate in extending and using these tools in new ways that we have not thought about. So why even do this? So let's step back and see why are we doing this data measurement-based analysis of developer productivity. I recently ran into this paper by Murphy Hill et al. That tries to answer the question, what predicts software developers' productivity? It sounds like a really challenging thing to answer. Now, what they did was follow and interview a few hundred software developers in 3 large companies. And then they evaluated various self-assessment metrics. And then they did a bunch of statistical analysis to determine what the developers thought affected their productivity the most positively and negatively. And the top 3 on average across all the developers in all the companies were job enthusiasm, peer support of new ideas, and useful feedback about job performance. So those 3, you can see that they have nothing to do with metrics that we can actually collect easily. However, looking down a bit more, we see that there are some software practice related things that they asked and rated. And for example, I use the best tools and practices to develop my software was rated This was a top factor at Google that contributed positively to the developers' productivity according to their own self-assessments. Now, there were other software-related factors that showed up in this, some that positively affected productivity were project bug finding process is efficient and effective, well-defined software process, reuse of code, such as by using APIs rather than duplicating functionality, mitigation of risks in the actual software design. Then there were some negatively rated, so negative impact on productivity, software that is very complex, software, the stack hardware to the top level changes rapidly. I'm sure that HPC people can relate to some of those. And requiring extensive documentation to use the software at different points of its life cycle. So some of those are less development process related, but they do touch upon things we consider. And the study's conclusions, I really recommend reading it. It's really interesting paper, is that the authors really pinpoint several things that we should consider if we wish to impact positively developer productivity. We need to be able to answer questions such as what makes software developers enthusiastic about their job, and what interventions can help, right? So a lot of these are human factors. I'm not a social worker. I can't really answer those from that perspective, but we can try to see what we can do with the data at hand. So the work in this webinar is part of two DOE-ECP projects, the IDEAS Productivity Project, which fosters and promotes software engineering practices for better software, and the XSDK project that develops the extreme scale scientific software development kit that incorporates some of the tools we are talking about today. So motivation and enthusiasm are great, but they're really difficult to quantify. And so on the other hand, we do have a lot of artifacts. We have the code and a lot of metadata that we generate as we develop code that may be related to productivity. So we are betting with doing this work that using some data is better than not looking at any data as we make decisions that try to improve our overall development productivity and code quality. And so our goal is to increase enthusiasm and motivation in those indirect ways, potentially, and hence result in more and better software. And the way we do it is by looking at the data. And so the webinar will introduce a flexible, efficient, and usable software framework is a strong word. It's actually not a huge amount of software yet for acquiring, storing, manipulating, and visualizing development-related data. And we show some of the capabilities here. However, we can't afford to spend the time to show everything. So hopefully you get a taste and look further. And contributions are welcome by anyone who is interested. And some of those applications that are mentioned here and at the end are used in examples in this talk. I have two parts in this webinar, and I'll pause between them. Part one is focused on mining development metadata, and part two is focused on analyzing code. So I will draw a little bit of a distinction between the two as we go along. Development data is any metadata that you create and generate as you use modern software development practices. And that includes Git metadata, the commits and associated data, forks, branches, pull requests. Developers who do these things are associated as well. Their personal IDs, issues, associated discussions. So there's some natural language parts to this data, and mailing list archives for projects that have longer histories than precede the existence of issue trackers. And our goal is to analyze available data to help formulate and answer questions. I don't claim to know all the questions that could be asked. And so part of maybe the most difficult part of this process is figuring out what questions to ask and then use the data to try to answer them in the effort to positively impact both productivity and code quality. So here's some questions so that we're not completely vague that we can ask. And some of them we can even answer with the tools we talk about here. If I adopt some practice X, how will metric Y be affected? Then you may wonder about your users or your developer communities. How active are they in what ways? Do they impact any part of your development process positively, negatively? What parts of the code base should be looked at first for refactoring? Is the project relying too much on a single or few developers? How are the developers' contributions split among the various portions of your package? And so on and so forth. You can keep asking. While it's not difficult to come up with questions that maybe nobody cares about, we thought it was a good idea to look at what people were doing in large scale project settings. And this is a little booklet that Pluralsight, which is a company that does educational services and products, put out. So they did research on several thousand software development projects in industry and identified 20 patterns that one, I assume project manager, the participants in the project should watch for in any software engineering team. And now this is industry, not HPC, but at least some of those patterns are pretty general and should apply to most software development settings. And they had the luxury of being paid to evaluate thousands of projects and their developers, while in the research community, we can't really afford to do that. So we leverage this wonderful resource to begin and give us ideas. And starting with these patterns, we can figure out which ones are relevant to HPC, which is largely open source, not proprietary software development, and very resource limited, unlike a lot of industry projects. We can characterize each pattern using data from revision control systems and developer communications. So we are not going to talk to anyone. We're just going to use publicly available data. And hopefully the outcome will be that we can inform some decisions on adopting new software engineering practices or addressing problems after they're pinpointed by this analysis. To make it more concrete, what is the data? What data do we have exactly to work with here? And what can we compute? The raw data, all of you know what it is, but things we can easily compute on top of that become derived metrics that we can use in this analysis. For example, rates, bug fix rates, and so on, correlations between different things, various commit-based metrics, issues that can be categorized either manually through tagging or automatically through natural language processing and so forth. So this is just to give you an idea of the really huge variety of what you can measure and express. And so before we dive into how it's done, I want to go through a few patterns so you get a clear idea of what this means. So the first pattern we tackled from the book, 20 Patterns, was the domain champion. And the names, I'm not a huge fan of all the names, but they mostly make sense. So A domain champion is defined as an expert in a particular area of the code base, and they know nearly everything there is to know about that domain, every class, every method, every algorithm and pattern. Um, so great. Why do we care about a domain champion? It could be extremely productive for somebody to be a domain champion and really own that piece of code and contribute to it actively. It may have code quality implications. And then what happens if the domain champion happens to be unable to continue to work? How do we detect it automatically? Now, keep in mind the 20 Patterns book, this was written for human analysts who go and evaluate projects and their teams. Here, we're talking about looking at the data directly. And so we have to figure out how to express some of these things. And so we take, for the domain champion, we decided to look at the changes that people did in terms of lines of code changed. And I will describe those metrics a bit more in detail later. Here we're looking at a particular granularity, which is files. Now you may say, well, domains are not files, but you can decide what you want to define the domain to be. It could be a class, a package, a module, a directory. Here we've decided on single files. Now you could decide on different metrics instead of lines of code changed, and we'll talk again more about those later. You could decide to focus on a specific time period. In this case, we're looking in February 2021. And then you have the champion metric. Who is that? Is that individual developers or sub teams? Here we're talking about individual developers in this example. Now, I have anonymized a lot of the projects, even though the data is fully publicly available, and there's a notebook I show in one of the slides where you can play with it directly. Because we have not yet published these results, the project names are omitted from some of these slides. So here, what do we show? We show that one of the developers, let's look at the second column, is really making a lot of changes to particular files. And the other important fact about this, these are sorted, by the way, so you only see the most changes and the most active developers. And here you see that also nobody else is touching those two files. So we could say the developer number 2 is the champion of these two domains. And positive things, very productive, possibly forever, but likely only in the short term. And then some issues, if you do have code reviews, include that you cannot, others are not familiar enough with this code domain to provide actionable, useful feedback in code reviews. And it may not be sustainable, that person to keep, especially if it's a larger domain, not just small pieces of the code. And actions that project teams can take is to try to try to involve the domain champion in other areas of the code if it's appropriate, or make an effort to involve other people in the domain if it's too large. Okay, so any questions so far? I'm gonna pause just a little bit. And I can't see the Google Doc at the same time as the presentation, so.
I think we're good to continue.
Okay, great. Another example from the book is unusually high churn. And this is pretty much what it sounds like. A lot of changes to single files or components that may potentially lead to development inefficiencies. And it could be a sign of normal productive development, especially sprints before some deadline, or it may indicate need for more developer resources on certain parts of the code. And they could be also people undoing each other's work, which is something we can easily detect. How do we detect unusually high churn? We can look again at the same sort of data, developers versus files. Again, we can pick a different granularity, not just files here, but for this example, we've chosen files. And then we just look at all the things that end up toward the left of this particular visualization. And again, we can decide to group. Instead of individual developers, we may choose to focus on sub-teams for larger projects. We also, again, have the time period that we can choose. And then the cool thing we can do with this data view of the data is we can choose a different churn metric. We could do numbers of files or lines of code, or some more precise change difference metrics, or anything else that you can count and quantify can become a metric for churn. So suppose you observe a very high churn, and in this particular example, the middle row here has everybody basically pounding on it, that particular file. So what do? We can consider refactoring the high churn project components into more independent pieces if possible, and then see if that fixes the problem. We can consider involving more developers in high churn areas that are dominated by a single person, and that would be this particular in this particular visualization. Now, keep in mind that all this really depends on the projects and what time period you choose. This happens to be over the entire project, which may not be very meaningful, and you may want to focus on a particular month or year. All right, so the next pattern, this is the last example. Now, there are many more, and there's some that we've thought of that don't exist in the book, and suggestions for others are very much welcome. But the last one I'm going to talk about here is in the zone. And this was pretty fun, actually. You want to figure out when are people most productive in a particular open source project. And again, you have the choice of time period, but you don't have the choice of the other axis. So we're going to show here in the upper right a heat map, but you can visualize it in other ways, of the days of the week, and on the x-axis the hours, 24 hours. And what we've tried to do is be very careful about local time zones. People are all over the world, so this is trying to use the person's local time. So it should be normalized, and it's looking in over entire project lifetime. So what's more interesting to also consider is how does it vary over, say, from last year or last month. Over the entire project's lifetime, we've shown one project over here where people are working mostly during the day, a little bit on the weekend, but not too much, and then in the evenings after dinner. Or if they eat later before dinner. But then in the bottom left, we show 12 projects, and you can see that it's definitely a thing that varies a lot among different teams. And you could also decide on your metric. Here we're looking at lines of code, cumulative, I think, yes. But you could also look at number of commits or pull requests or other metrics, and it's equally easy to generate this. And the high productivity, I mean, one things you can do for all these patterns is actually acknowledge all the good stuff that is going on, and make developers aware that you appreciate this. Things that you can watch for and act to prevent is burnout and work-life balance. If your project happens to involve people working mostly at night, maybe that's okay, but maybe there's something else going on. And then there's some projects that are fairly stable and not much is going on, and that's fine. And I already mentioned, we can acknowledge the consistent performance, and you can acknowledge positive change in people who may not have been doing so well. And You can also avoid scheduling meetings during the most productive times for your own team that you know based on this analysis. Um, in this heat map here, we've actually put an average of all the projects that we have um, from the ECP publicly available projects, and it's kind of interesting that the lighter numbers here are higher values. It seems that most of the work is happening in roughly after work, after 5 p.m. hours, which is kind of an interesting observation.
When,
So
when I have there are a couple of questions if you'd like to
yes,
them now.
yes, please.
So, okay, first, does the size or maturity of a project affect the way that your analysis methods work?
That's a great question. The size does not very much. The maturity does. For example, there's some, and I don't even, these are anonymized, so I don't remember which project is which in this bigger diagram, but there's just not, in some of them, they're pretty stable, so there's not as much active development. There's also the different philosophies of how you commit and push work can be reflected here. So yes, maturity definitely matters. How you do the analysis doesn't. You may decide to focus on different metrics or different time periods, but the tools work just the same.
Right.
Size doesn't matter at all, and we'll talk about that a little bit.
Okay, so there's another one here related to the LOCC metric.
Yes.
Okay.
Go ahead.
Some commits make global search and replace.
Oh, great question. I'm going to defer to a slide that talks about some of that.
All right, so then some commits make global search and replace type changes, for example, rename an important internal class. That might touch a large fraction of the code base. However, such changes are not well correlated with developer effort recognition. Do you try to recognize or filter this type of activity during analysis?
Of course, yes, great question. And I will answer it. I believe it's the next slide. Yes.
Oh, good. So I see people are typing more questions here, but continue, Bojana, please.
Great. Now we have some examples in a notebook that you can see the link here. Hopefully it's been on long enough. And the software itself is always changing, and we're always improving and updating. Here's the repo. Just a quick, I'm not going to talk much about implementation. Just a quick note with the important parts are that we do import all the data into the database, and we automatically update it every week right now, but we can do this more often. And the reason we did that was that using whatever APIs GitHub and GitLab and others provide was not efficient, and especially if you wanted to use the data over and over again. Moreover, if you're working locally, which you prefer to do for speed, we'll create a local data cache for the data you're currently using, so you don't have to go to the database over and over again. And then we have a few simple interfaces to the patterns so far and the visualizations that we're able to do. The whole thing is based on pandas. I'm sure it can be simplified even further, but I think at this point it's getting to the point of being super easy to do certain things without really having a huge learning curve. And if you want us to import your project, please just ask. Can be done very easily. Okay. Change question. This is very important, right? So lines of code. Now the metrics that you've seen so far in the examples, we're using the LLCC, which is defined as edited lines plus deleted lines plus added lines. And so yes, if you do a global search replace, this would look large, right? Or if you don't ignore white space, especially reformatting can make you the best, most productive person in your project. Now, the reason, and so we don't want to have just that as a metric of change or productivity. And so what we do is to incorporate a variety of change metrics which are currently based on this wonderful text distance Python package. But, oh, I'm sorry, there's a typo here. Page should be package. And you can see that for the exact same analysis here, we have two heat maps that are identical in every way, except the top left is using lines of code changed, and the bottom right is using cosine distance of the before and after codes. And again, those are not actually, so they're treating the changes as text, but they're obviously not going to change, they're going to reflect global renaming much more accurately and similar types of changes by giving it a much smaller distance value, since most of the code did not change, even if every single line changed. Okay, so hopefully that answers that question. And notice especially here, there's this developer in the first column who's basically doing mostly those kinds of things, could be automatically generated changes of various sorts, such as reformatting. Did that answer the question? I hope that was okay.
Okay, and I think that it seems there is a question related to this one here, the one that I just answered. So the participants wondering if there might be ways to distinguish between productivity changes, such as blocks of codes that are added and remain relatively stable,
Yes.
versus potentially unproductive changes, like
Oh,
blocks that are constantly being modified by both additions and deletions.
yes, that's a great question. I know you're saying blocks of code, which refers to the granularity. I've only shown you files so far, but we have actually worked on and implemented function-based, function level change analysis. And if you want to go finer grain, then that doesn't quite exist yet, but it can be done in the near future if people have interest. So at the function level, we can identify functions that haven't changed for a while or are changing a lot. Yes. And they can be a separate metric, stability metric we can associate with that. That would make it easier to track. And this is actually bringing me to the time dependence of all this data. Time series of all these, of the raw data looks like a heart attack. It's very jagged and noisy and ugly looking, and you can't really make much sense of it. So really for all of these types of, whether it's a raw metric or something you derive, such as, for example, if we create a new stability metric for the project of how much it changes over time, we can visualize it or just work with it, but we can also smooth it before visualizing and working with it. And this shows a few of the available smoothing functions of moving averages, and one more visualization in the bottom right, which tries to put more data into just the 2D plot. So here, the interesting thing about the bottom right is it's showing two change metrics at the same time. On the y-axis is doing the lines of code changed, as I defined in the previous slide. And the size and color of the bubble is the cosine difference of the change. So what you can see in this really high, small bubble is that a lot of lines changed, but the change was not significant. Whereas this dark, bigger bubble is lower, so not so many lines changed, but the change was the most significant one in this particular project's lifetime. And you can also easily spot significant things happening. Obviously, you may already know this because you're a developer in this project, but maybe you don't, and maybe it's interesting to study what are these big changes. And then what this lets us do actually is not just look at the bubble plots, but it lets us focus our subsequent analysis on more significant periods. Instead of here, we're going over the entire project lifetime and we spot this 2020 very significant change happening, and then we want to study that further with the rest of the analysis that we have on what kind of change is it, who did it, was it done, was it tested, et cetera, et cetera. So here's 2 projects anonymized. Again, they're publicly available, so you could reproduce this after getting the names, but we can zoom in and study further that particular period of interesting things happening. And speaking of interesting things, I show here a fun thing. Now, the visualizer component of our toolkit doesn't directly support this plot. I did not build in, I did not think the emojis were generally useful built-in capabilities. So that's a little bit messier Python code to produce, but not too hard. Showing how 4 projects behaved over 1 year for 3 different cases, 2019 in blue, 2020 in brown, and the average is a green dotted line. And those 4 projects exhibit very different things during the pandemic, before and after. And it was interesting actually to see, I mean, I don't know if I'm not part of those projects, but it seemed like an interesting way to evaluate how changing to work differently affected the productivity in terms of, this one is cosine difference changes. So not lines of code, so a bit more accurate. As I mentioned before, you may want to refine how you look at what's being changed. So one thing that we published, and here the project names are shown because this appears as a paper in 2020, which involved other components, not just the data analysis. So this was our early attempt at doing this categorization of the code package structure. So we have 7 different categories that basically defined by looking at the code itself and labeling different parts of it. Now, it would be great if we could do this more automatically, but currently it's still manual labeling of the different components, and so it may not be 100% accurate, especially according to the developers who know best. But it's very easy to maintain once you've labeled it. So that might encourage people, I think, to provide even more metadata that can help this process. And what it's showing, for example, is over time, again, we can pick the period, but this is over all available data. How much time is being invested, or in terms of the changes, but how much is being invested in different things like documentation, tests, and then we also had to identify external software that was just being included because that can represent a very big fraction of the commit data. So one thing to monitor, I guess, is to see, well, maybe we're devoting too much time to, well, I don't know, you wouldn't say math, but maybe not enough time is being devoted to testing. This is not true for any of these projects. As you can see, actually, for all these projects, testing is becoming more and more important, or holding steady at some rate. And here you can also see project maturity as well very easily on that kind of visualization. Any questions?
No, I think we're good.
All right. Then we had a few things that address productivity metrics that did come up in this 2021 paper. How are people feeling about things? Unfortunately, we didn't talk to anyone. We basically looked sentiment analysis, which is not very reliable when you're looking at software developer emails and issues. And so this was a fun preliminary thing that may not be ready for prime time yet, but I do bring it up because it's pretty interesting. And we here look at, is there any sort of even time displays correlation or negative correlation between sentiment scores, which are just on a rank, on a rate of 0 to 1, and different effort estimates we're able to compute. And is at least looking at Petsy, it seems like when people get unhappy, they then become very productive. But that's just half joking here. Don't think we can really conclude much yet. We can do the analysis and refine it to see if we can make predictions. But right now we're just observing. For this particular project, VTK, we see that happiness follows great bursts of effort. Now, again, we're not really connecting the individual developers here to who did the changes and who was happy. So this is really coarse grained. And that's it for the first part. Any questions on the metadata-based analysis?
See here, there are two questions left. How do GitLab dashboards help HPC-specific metrics?
The actual GitHub and GitLab dashboards, you mean the web interfaces they have? Or what we are doing with the data? I'm not sure I understand.
Well, maybe the participant can add some more info there in the question. So let's move to the other question. It's related to this. Okay, so doesn't the zone only include lines of code merged into main branches? There are there are likely many PRs that don't get addressed where people spend a significant amount of time.
Yes, and we are doing exactly that analysis now for one of the projects. Yes, you can break down the analysis into individual PRs, for example, or consider a subset of branches. That's currently, we're trying to make that easier so you don't have to know SQL. But yes, that's a great question. And how many PRs are started and abandoned? That kind of thing is very interesting and useful to know. And how much effort.
Concerning the previous question, Boyana, it's a web dashboard for GitHub.
Yeah, we don't, I'm not sure. There are better tools actually, but they're not free. We are working on our own web dashboard, obviously, that is more customizable because you can add new metrics easily. I'm not aware of people relying heavily on the GitHub and GitLab dashboards, but and they're somewhat limited, and we don't really use them much ourselves. I don't find very much value there. They show a few canned things, and yeah, so my answer is I'm not sure, but I don't think they're very widely used.
Yeah, please continue then, Liana. Thank you.
All right, so this is a shorter part. I do want to talk about code quality a bit because we want to also maintain and improve that as we go. And we obviously can do different types of analysis, but the main goal of code quality analysis and changes is to make sure that there are fewer bugs, and in general that will save effort and lead to better productivity. There are many general purpose tools for code checking of different types, and I just want to make sure that everybody here is aware that they exist. I didn't write those. They are part of different open source tools, for example, Clang. And so I do mention them here in case you did not know, and show an example to show how easy it is to start applying them. And Clangs support actually two different types of tool sets that are both extensible and operate at different granularities. There's the Clang Static Analyzer, and can do very complex analysis. But it does require more compiler knowledge to extend if you want to extend it with custom things. And then there's Clang Tidy, which is a little bit less global, but very easy to extend. And we are showing, actually, we're developing some examples to help people do their own analysis. Fortran is behind as usual. There are some tools out there, and we also work on adding to that. So here's an example commit workflow that you may already follow. And this is an example from the XSDK codes that I showed that they may already be doing most of these steps anyway. But then what we would insert is, if you're not already doing any of the quality checks, you would have a few steps to look at format, Clang tidy passes, Clang static analyzers to look for memory errors or other problems, and then insert some specific analysis for your project, this case XSDK, and then move on with your usual builds and checks. This is just an example workflow. I'm not saying this is the one. How do we do this? We integrate both static and dynamic analysis. And right now into the XSDK, we are going to finish documenting in this week, basically, the tools that we have developed and wrapped. And so why do we do this? Statically and dynamically. Static program analysis allows you to consider all possible executions. So that's really the big takeaway here. Regardless of how many tests you have at your disposal, you're able to look at the entire code with all its paths. And Clang Tidy and the Clang Static Analyzer offer ways to do that. And dynamic program analysis requires you to actually run something. You've used tools, I'm sure, such as Valgrind, and there's Clang and LVM sanitizers, which only examines a single execution path at a time, and it requires building and running your code. Now, what we are doing in our efforts and is to document existing general tools, such as the Clang tools and for CC++. And then for dynamic, we are trying to show how you could write simple checks for your own project. So I'm not going to go into too much detail of how it's done, but the goal is that it should be a minimum extra burden on your build. Fortran, as always, is a little bit behind, and we're trying to bring it up to speed with at least some of those analysis. So what does it mean to do this as part of your workflow? It may be as simple as just typing scan build in front of your CMake and make commands, and other build systems are supported. So this is the built-in Clang tools. And you will get a report, a very big report potentially, which can be a little bit shocking. Once you get used to it, it's quite easy to realize what it is you need to do. But initially, at least, it's a little bit overwhelming if you have not been doing this on a regular basis. So one of our future things that we plan to do is to sort of generate more bite-sized pieces of what to do with this information. Then what if you want special checks? Do you need to be a compiler expert to write your own checking? And the answer is no. I'll show you a PETSI example. PETSI is a large C toolkit of nonlinear and linear solvers. And we have looked at its documentation for developers, so developer guide, and extracted a few of them verbatim here. And they're mostly syntactic. Variables and macros. Macros should be capitalized. There should be underscores between different words, etc., etc. You should never compare rank to 0 in MPI codes and so on. So pretty simple, but Clang Tidy and other tools don't know what to do with that, don't check for these things. So we implemented some very simple libtooling based checking for these. And here we show some examples of exceptions that have been caught. For example, that macro name is not capitalized in this one, or there are no underscores where there should be, and so on. And I'll skip this because it's pretty straightforward to see the implementation. Rule value, so just looking at, well, what happened with all these 7 or 8 rules that we were checking over the entire history of code changes. And obviously you want to bring most of these down to 0. Now, this is not nice because we just did this, and so the PETSI team hasn't had a chance to do anything about it. But ultimately, what you want to do is make sure that all of these go and stay as close to zero as possible. And to summarize, this is basically set of tools and associated examples that look at data that we can obtain easily, publicly available development data. And in some cases, we store it in a database, and in other cases, we do not. And for example, the code quality checkers, they don't use a database. They just use your code wherever it's sitting. And we provide examples, and then I have some locations of where these things are being developed and documented. The mailing list analysis is available if you really want to look at it. However, we have not quite updated it to use our existing database, and so it's less up to date. But that basically has the sentiment analysis and other such functionality I mentioned briefly. And to summarize, we've shown a few examples of how we can use data, and the associated tools are available, and we really hope that you can try them out or contribute or both. And I want to acknowledge the many uh, students and colleagues who have contributed to this work. So thank you very much.
Thank you, Boyana. Very nice webinar here. So there is a question here. Before I invite the participants to unmute themselves, do you try and distinguish between changes to code files and the in repo documentation, including comments, readmes, markdown files, etc.?
Yes, and not comments. So that's a good question. I'll go back to a slide where we do show some of that. In this particular case, we try to differentiate documentation, right? READMEs, HTML, things like that, LaTeX, PDFs. So yes, but in general, no. So in the lines of change though, so for example, any of those plots here, what they do is they look at only what we consider code. So there is a set of file suffix file suffixes that we consider, and only that set. And so yes, they would not consider readmes, for example, but you can change the list of suffixes to consider to make that do whatever files you want.
So now I'd like to invite the participants who would like to ask questions directly to Boyana, just by, people can unmute themselves.
Hi there, I'm Vanessa. I'm from Lawrence Livermore National Lab. Thank you for giving this talk. I really enjoyed seeing all the cool metrics. I was interested if these metrics are very sort of project centric. So the projects are chosen, I'm wondering if you're looking at metrics about like how well the projects are doing with engaging with the outside community.
So that's a wonderful question. Depends on how you define outside community, right? We have not done that specific analysis, but I think that it is possible to do this both through looking at the emails or text-based communications and the code references, so what external things you're using in your code. And I think some of our colleagues at Sandia were looking at some of those types of analysis. But yeah, that's a good question. And no, we don't really do that very much, except from the point of view of user mailing list analysis.
Cool, thank you. And you could probably also look at, things that are maybe a little harder to measure, but like social media, how the extent to which projects are interacting with like people at conferences and having hackathons and things like that.
Yeah, maybe somebody. I'm a little bit allergic to social media data analysis, but Yes, I know. It can be done, definitely.
Any further questions from the audience?
I should say though, if you're interested in combining this with other types of data that you're excited about, I mean, my group is always really happy to collaborate and do new crazy things.
I guess I'll ask a follow-up question to that. What is like the best way to kind of interact with your group? Like where's all this happening on GitHub that I could go and open initiative
Oh yeah,
and start a discussion?
let me go back to that place. I don't you can still see it hopefully. I think I had it in the conclusions. Well, first of all, Googling my name is the easiest because I'm the only one. But if you want to go to this one IDEAS project, so the IDEAS work which is most of this talk, is at this GitHub website. But you feel free to just get in touch with me directly if you want.
I'd like to mention that the slides are already available there on the registration, the event page. Any additional questions? If not, I'd like to share here. I'll take the sharing back, Bojana. Okay.
Yep, thank you.
Just to announce the next webinar in the HPC VP series. It's going to be on August the 4th, a little more less than a month from today. Software engineering challenges and best practices for multi-institutional scientific software development. And the event has been already posted. Please give us feedback so we can improve this series. And the slides and recording, the slides are already available. The recording will be available soon online. So, and if you have suggestions for future topics, right? For topics for future webinars, those suggestions are welcome. Thank you very much, Bojana. Thank you for the participants for joining us today.
Thank you very much.